Hey guys, welcome back to chapter 11. So what we're going to do in this first video is introduce our first of the four intermolecular forces. The first one being London dispersion. So London dispersion is the weakest of our intermolecular forces. London dispersion is also exhibited in all atoms and all molecules. So everyone exhibits London dispersion forces. Some molecules have the additive effect of the other ones, but all molecules have London dispersion, the weakest of our intermolecular. So London dispersion force is a temporary fleeting attraction between non-polar molecules or non-polar atoms. So big things to focus in on here. Fleeting temporary attraction. So as I introduced before, intermolecular forces are going to have to do with polarity, right? So positives attracted to negative. So during this London dispersion force, there's going to be a very temporary, very fleeting, very weak separation of charge, and that's going to cause these molecules to be attracted to one another. Okay, so what we see here is three snapshots, three frames of a helium atom. So helium atom, here's our nucleus, here's our two electrons. So helium being the second element on the periodic table, has two electrons. We also know helium is a non-polar atom. It's one of those noble gases, right? So relatively inert, happy with the two electrons, and its valence shell, full valence shell. So happy, stable, inert gas at room temperature, non-polar, okay? So what happens when we have a whole collection of helium atoms in a beaker? So those electrons we know are dynamic, right? They don't just stay in one place. So if this is our electron cloud or where our electrons reside, these electrons for the most part are going to try to stay as far away from one another as possible, right? So frame 2 would probably be the most ideal situation here. We've got two negatively charged particles. They want to be as far away from each other as they possibly can. But they're going to move around. So they're going to move over here, move over there, move over here, move over there. Every once in a while, what's going to happen is these two electrons are going to be moving and they're going to, end up on the same side of the atom as one another, okay? So if we look at this atom here, we've got two electrons that are relatively close to one another, absolutely no electrons that are on this other side of our atom. What this is going to cause is a very temporary, a very fleeting fluctuation in the electron distribution, okay? So if we look at this snapshot of this atom, we're going to have a lot of negative charge over here. Remember, our electrons are negatively charged. So with the electrons comes that negative charge. And over here, in the absence of the electron, we're going to have that fleeting positive charge, okay? So we have that partial positive. So we're going to have this moment where the left-hand side is negatively charged partially. The right-hand side is a partial positive. So we're going to have this temporary dipole moment, this temporary distribution of a positive and negative charge. As fast as this distribution happens, boom, it's gone. So that's what I mean by temporary and fleeting. They're going to be together. Oh, crap, we're too close. We're going to get separated apart. It happens that fast. But during this momentary dipole, during this momentary fluctuation in the distribution, this is going to induce a distribution in the helium atom that's next to it. So right here, we see a partial positive. And if there's a helium atom sitting here to the right, the electrons are going to go, ooh, positive charge. Let me come over here. And so in the next atom, it's going to be this fluctuation in distribution. And as soon as that atom fluctuates, the next one's going to fluctuate and so on and so forth. So it's going to induce this attraction in other molecules. So it might look something like this. So this might have been the original helium atom. So again, we see, oops, these electrons got really close together, partial negative over here. Well, this helium atom that was sitting right here, the electron may have been here, and then it goes, oh, look, positive charge induces that temporary fleeting dipole. And then this one over here goes, oh, look, positive charge. And it induces a temporary fleeting dipole moment here, okay? And as soon as this one becomes a dipole moment, this one's done. And as soon as this one's a dipole, or as soon as this one's a dipole moment, this one's done. So it's temporary. It's just going to happen for a moment, and it's going to go back to being a neutral atom. So temporary fleeting attraction. This happens in all molecules, whether they're polar or non-polar. We introduced this in a non-polar molecule because this is the only type of intermolecular force that happens in a non-polar molecule. So one of the things that you're going to do for lab this week is you're going to do a polarity, determine the polarity of molecules. So this is a skill that we're going to go back to from General Chemistry 1 that I'm sure many of you need a refresher on. So the first thing you're going to have to determine is this a polar molecule or not? If it is not a polar molecule, London dispersion is it. That's all we have to deal with. If it is a polar molecule, well, then we have to think forward to some of the other intermolecular forces. Okay. So what are some of the factors that determine the strength of London dispersion? So what we're going to talk about at the end of this chapter is how these intermolecular forces affect properties. So properties like boiling point, melting point. Is it a liquid at room temperature? Is it a gas at room temperature? So we're going to need to know how strong are these intermolecular forces. So one of the factors that determines the strength of London dispersion, and really this is going to hold true for all of the intermolecular forces, is first the size. So the larger the atom or the molecule, the stronger the London dispersion is going to be. The greater opportunity we have for this instantaneous dipole to occur. So let's think about the size of our atoms. So here we're going to look at our noble gases. So we're just going down 18 or 8A, helium, neon, argon, krypton, xenon. All of these are neutral atoms. So the only intermolecular force they have is the London dispersion. And remember, as we go from top to bottom, they get larger. So the atomic radius increases from the top to the bottom. Why? Well, remember, we're adding shells. So for helium, our valence electron is in the 1s shell. It's in the first energy level. When we go to the valence electron for neon, we've added a whole energy level. So now we're in the second energy level. And for argon, we've added another energy level, and these superimpose on one another. So as we move down the periodic table, our valence electrons get further and further away from the nucleus, and our atomic radius gets bigger and bigger, okay? So larger the size, the stronger the intermolecular force. The reason for this is because the valence electrons for xenon, for example, are a little bit more susceptible to outside influence than our valence electrons for helium. So remember, valence electrons are negatively charged electrons. We've got our positively charged protons in the nucleus. So if our protons are very close to our valence electrons, those protons are going to shield or protect the electrons a little bit. So they're going to have a little bit more influence on those valence electrons. Valence electrons are going to be less susceptible to outside change. If we come out here to xenon, now we've got a great distance between our protons in the nucleus and our valence electrons way out on the outside of our xenon. So the protons are going to have less influence on those valence electrons, and those valence electrons are going to be hung out to dry a little bit, right? They're going to be kind of hanging out in a further energy level, more susceptible to outside influence. So as we get larger in size, we're going to be more susceptible to this London dispersion force. So the larger the atom or molecule, the stronger the London dispersion attraction is going to be. The other factor that's going to determine the strength is going to be the shape of our molecule. So when we talk about shape, we're going to talk about surface area. So think of a crumpled piece of paper, crumpled all up in a ball, and a flat piece of paper laying out on the desk. Flat piece of paper is going to have a lot more surface area. So a lot more opportunities for me to touch that piece of paper. A crumpled up ball is going to have a smaller surface area. So less opportunity for me to touch the surface of that paper. So a sphere is going to be the shape of the smallest surface area. Okay. So more surface area is going to give us more opportunities for these interactions to happen, for these fleeting momentary dipoles to take place. Okay. So this would be an example of our crumpled up ball. This would be the example of our flat piece of paper. So in our crumpled up ball, if these two molecules are in a beaker together, the only opportunity that they would have to interact with one another, the only opportunity where they would have for this fleeting attraction to take place is at this point right here. So this is the only point on these two molecules where this dipole interaction could take place. For these two molecules, again, these are isomers. So same number of atoms, same molecular mass, structure, the way they're put together is different. For these two molecules, we see this nice flat surface here. So the opportunity for an interaction to take place could take place over any position in this area right here. Okay, so it's not just one singular point where this London dispersion interaction could take place. It's this whole big line right here where the London dispersion could take place. So more surface area, more opportunities for interaction. And what we're going to see is this guy right here would have a stronger intermolecular force. This guy right here would have a weaker intermolecular force, or stronger attraction here, weaker attraction here. Okay? So those are two factors that affect London dispersion, and really they're going to affect all of the intermolecular forces. So that ends the discussion of London dispersion. Just real quick recap. Weakest of the intermolecular forces, all molecules exhibit London dispersion. Non-polar, this is the only one they have. And then factors that determine London dispersion are size and shape. Hope you guys found this helpful.